Hello and welcome to this video about rectangular waveguides. This is the 5th video in this series, and in this video we'll derive equations to find the total electric and magnetic fields at all of the points in the waveguide. To do this, we'll need to expand two of Maxwell's equations, called the Maxwell's curl equations. I've just written them out here. So now to expand the first of these two equations. We'll expand it out in Cartesian coordinates, which is a good coordinate system for a rectangular waveguide. It does look fairly messy when compared to vector calculus equations, which look so much more compact. Now to decouple this equation, the expressions for each unit vector can be separated out. Decoupling this equation gives us these three equations. We can substitute gamma for this operator in each of these three equations. Making this substitution gives us these three equations. Now to expand the second of Maxwell's curl equations. This is what the equation is after being expanded out into Cartesian coordinates. And we can decouple each expression for each unit vector, I hat, j hat, and k hat. These are the three equations decoupled from the expanded curl equation. We can make this substitution for this operator in all three of these equations. And so we get these three equations. These are the 6 equations that we've derived from the two Maxwell's curl equations. So the next step is to manipulate them so as to get these equations, which are Ex, Ey, Hx, and Hy, being expressed as functions of Hz and Ez. We've already used these equations before to show which modes can and can't exist. It must be noted here that when Hz and Ez are both 0 everywhere in the waveguide, then all of the fields inside the waveguide must be 0, and so the TEM mode can't exist inside a rectangular waveguide. Now to step you through a derivation of one of these equations. We'll start off with these two equations here. We'll manipulate the first equation to get the next one, which is Hy as a function of Ex and Ez. Now we have Hy as the subject of this equation. We can do a similar thing with the second equation. We'll get Ex as a function of Hz and Hy. And so Ex is the subject of this equation. We can then substitute the first of these two new equations into the second, which gives us this messy looking equation. We can expand all of the brackets of this equation. Then we can manipulate it a bit more. You can already see that Ex is going to be expressed as a function of Hz and Ez, which we have found earlier. Ex can be made the subject of this equation, and then this equation can be tidied up. I'll just write this equation out again here. We can define a new variable h to be equal to this quantity, so as to help tidy up this equation a bit more. And the propagation constant gamma can be expanded out to its complex number form. We can then substitute these variables into the equation at the top, which gives us this equation. I've circled the variables that were substituted in coloured circles. Alpha is set to 0 because the wave is propagating as a sinusoidal wave and not attenuating. And so this is the final form of this equation, and the other three may be found in a similar way. Now to find Ex as a function of x, y and z in the waveguide, in the TM mode, where Hz is equal to 0. And this is the equation for Ez in the TM mode. This is what Ex is in terms of Hz and Ez. We can then substitute these values for Ez and Hz in to get Ex. Making these substitutions gives us Ex being equal to this expression. Then evaluating the differential equation gives us this value for Ex. After tidying this equation up, we get this value for Ex. Similarly, we can derive Hx for the Tm mode. We'll start off with these three equations here. We'll substitute the first two into the third, which gives us this messy expression for Hx. Evaluating the differential equation gives us this equation. And then we get a tidied up formula for Hx in terms of x, y and z. So these are the two equations for Ex and Hy in the Tm mode. Hy can be derived in a similar way to Ex and Hx. This is the wave impedance of a material which has these values for epsilon and mu. The wave impedance is more properly defined to be equal to the magnitude of the electric to the magnetic fields, which are perpendicular to each other. We can substitute these two top equations into it to find the wave impedance of the waveguide. After making the substitution, we get a fairly messy expression, but you can already see that most of the terms should cancel, thus giving us a nicer expression. And so they do cancel, and you might be able to see which variables don't. So we finally end up with this equation for the wave impedance of the waveguide, which looks very simple, but would look a lot uglier when beta is expanded into a function of omega. I'll just write this equation out again at the top of the screen. This is the formula for gamma in terms of the radial frequencies. It can double up as a formula for beta, because in this case they are equal. Making this substitution gives us this new equation. After tidying it up, we get this equation. This is the wave impedance of free space. In a waveguide, the wave is propagating through air, which is very nearly exactly the same as free space when it is measured as an electromagnetic material, so this substitution may be made. And this is the wave impedance of the waveguide in terms of the frequencies. We can do a similar calculation for the TE mode. In this mode, Ez is 0, and Hz is equal to this. This is what Ex is in terms of Ez and Hz. Making this substitution gives us this value for Ex. After evaluating the differential equation, we get this expression. The expression containing Ez vanishes. Tidying up this equation gives us this formula for Ex in the TE mode. We can do a similar calculation to find Hy in the TE mode. Here are the equations that we need to use. So making the substitution and tidying up the expression gives us this formula for Hy in the TE mode. We can now find the wave impedance for the TE mode, which is different to the wave impedance for the Tm mode, using these two formulas for Ex and Hy. This is the formula for the wave impedance. After substituting these first two equations into the third, we get this equation, which looks messy, but also looks like most of the terms will cancel out. This is what the wave impedance is after we simplify this last expression. Now we have to use this equation to find the wave impedances in terms of the frequencies. This is what beta is in terms of the radial frequencies. We used it before. We can assume that beta is equal to gamma when we use it. Making the substitution gives us this equation. We can simplify this equation to be this. and we can substitute the wave impedance for free space into it, because the waveguide will have air in it, which has the same wave impedance as free space. We can also find the wave impedance as a function of the frequencies. I've gone into more detail earlier as to how I can get this last equation from the first, using simple algebra. So now to see why the TEM mode can't exist. This mode supposes that both HZ and EZ are zero. This is the equation describing what EX is in terms of HZ and EZ. If we substitute the first two equations into the third, we'll get EX for the TEM mode. After making this substitution and simplifying the expression, we get that EX is zero. We can similarly find that all of the fields are zero inside the waveguide in every direction, and therefore the TEM mode can't exist inside the waveguide.